Hi, welcome to the first video in chapter 11 where we're going to discuss alkenes, which are also known as olefins. That's kind of an older word for alkenes, but it's used a lot, or at least I use it a lot. I don't know what that says about my age, but also in this chapter we're going to be introduced to infrared spectroscopy, which is really useful to identify alkenes. And to be honest with you, I'm not super sure why the mass spectrometry stuff is in this chapter, but I also understand maybe there wasn't like a really good any other place to put it in there, so it's in chapter 11. So let's get into it. Just hopefully you appreciate that meme right there on the first slide. First thing though, like I do kind of want to go over the nomenclature with you on this, because unlike, say, the last nomenclature stuff we talked about with alcohols, which were hopefully fairly straightforward, this is a little bit, slightly bit more involved, so it's worthwhile to use some lecture video time to go over this. So the main thing, right, is that I want you to know the alkene names end with "ene" instead. Alkane ends with "ane", A-N-E, but you just replace that with E-N-E, and that's pretty much it, right? That's the new thing. Now, of course, the other thing is you do have to indicate where the alkene or the double bond is with a number, and we'll look at an example of that. I do want you to know that alkene is not a very high priority functional group, and when we say priority in this case, it's not in the same sense as we talked about for like RNS assignment, but this has to do with higher priority functional groups get numbered lower, get assigned a lower location number, like 1 or 2 or 3 or something like that in the chain, rather than a lower priority functional group. And that gets a little bit more important next semester when you start discussing like higher priority functional groups like ketones, carboxylic acids, and so forth. And alcohols and so you might see an example where in the same molecule you see alcohol and alkene at the same time, and that would end with enol. Okay. And the other thing that's kind of new and important is that there's a stereochemical implication here. Cis versus trans and E versus Z, which we'll get into it. So that's kind of the overview. Now, this structure on the left, that has 1, 2, 3, 4, 5, 6, 7 carbons. So does it hopefully make sense to you that it is heptene, but we do need to indicate where this double bond is, and it starts, let me see if I can, it starts at the first carbon here, right? If we start numbering from the left. So for that reason, this would be 1 heptene. Now, this one on the right, it's still closer to start numbering from the left instead of to the right. 1, 2, 3, 4, 5, 1, 2, 3, 4, 1, 2, 3. So it's better to number from the left. So this would be 3 heptene. Now, here's the twist. This name is actually kind of inaccurate, or I should say it's incomplete. And can you tell what is incomplete about it? And the reason why it's incomplete, is that this structure is also 3 heptene, and the two are different, right? They are kind of rotated around the double bond, but remember the double bond, right? Like they involve a pi bond. Pi bond has that side-to-side overlap of p orbitals. So for that reason, they can't rotate, because if they rotate, if you rotate one of the p orbitals, then you're not going to have that side-to-side overlap. That means you just broke that pi bond. If you break a bond, it's no longer the same molecule anymore. So you can't go from this molecule to that molecule, or not easily anyway, without some kind of a chemical reaction. And so we need a way to distinguish these two because they're not exchangeable. Double bonds do not rotate. And it would be more obvious to you if you make a model. Yes, your molecular model still is important and helpful even at this stage because it shows that you'll notice that double bonds cannot be rotated with your model. Now, so how do we distinguish these two? We're going to use the cis and trans designation. When the two groups are on the same side of the double bond, we would call that cis. Okay, and then when we say they're on the same side, here's the double bond, and on this side you got this substituent, where this part of the chain and this part of the chain are on the same side of the double bond. Whereas in this molecule, this part of the chain is on that side of the double bond. This chain is on this side of the double bond. It's on the opposite sides, hence trans. Part of the arrow is kind of obscured here, sorry, but B and D on this olefin are said to be trans, whereas A and D would be A and D here. Sorry, my face is covering it. This is one of those moments that makes me wonder, like, is it a good idea to show my face in these videos? But like, that's kind of the default in PowerPoint, and I didn't want to change it. Not that it's such a great face to look at, but I'm just gonna leave my face here. Okay, so A and D, that those two are trans to each other. Okay, you can look at the PowerPoint file on for some reason I was going to say Amazon, but Canvas, on Canvas to look at the notes that are hidden here. But and maybe this meme helps you. Right, cis in trans. All right. Now the excuse me. Now, what about this molecule? If you have a branch or some other substituent on an alkene molecule, you just have to add that with the number location. And this is the way you would write that name, trans 2-methyl-3-heptene. So this would be the 2, 1, 2, 3, 2 position. Okay. Now, what about, what if you had like another functional group like alcohol in there, yeah, so let's think about that. Alcohol is a higher priority functional group, and so for that reason, we want to start numbering the chains so that the alcohol location gets as low of a number as possible, right? So we need to number from the right side this time, which means the alkene's location now is carbon number 6. And with the RNS included, this would be the name of that molecule. Our 6-heptene-3-ol. Now, the 6 here refers to the ene or the alkene, and the 3 refers to the location of the alcohol. Now, if you are really into the newer IUPAC scheme, you could name this R-hept-6-ene-3-ol, but I don't prefer that. So anyway, so here's the name for that. Now, what if we had a situation like this, right? I meant to add in some animation here and I forgot, but sorry. This is, right, kind of a problematic situation because you can't really name this cis or trans because this ethyl and the propyl are cis to each other, but this ethyl and the bromo group are trans to each other. Does that make sense? So these two are cis to each other, but these two are trans to each other. So should you call this cis 4-bromo-3-heptene or trans 4-bromo-3-heptene? It's not clear, and so there clearly needs to be some other way of naming the stereochemistry designations when it comes to like tri-substituted olefins, right? So the way you do that is the EZ method or the EZ uh, configuration. Okay, and like the name suggests, I hope this is pretty easy for you, especially after you've learned about the R and S configurations. Now, what you do is kind of similar to um, the RNS. So what you do is because each of these is a stereocenter, right? Remember, stereocenter, once you swap the two, it becomes the other stereoisomer, right? So these two carbons of the olefin are stereocentered. So um, you want to uh, assign priorities to the groups attached to each stereocenter. So this carbon, this has a carbon and a hydrogen attached to it. Same rules as RNS. Carbon is higher atomic weight, or I should say atomic number, so that's priority number 1, hydrogen number 2. And on this stereocenter, this bromine is priority number 1, carbon is priority number 2. And then you look at which way the highest priority group on each stereocenter is pointing towards. On this carbon, it's pointing that way. On this stereocenter, it's pointing this way. They're the opposite sides of each other. Hence, we'll call this Entgegen, and that's a sort of a product of back when organic chemistry was mostly developed the most in Germany as opposed to say the United States in the 1800s. The word Entgegen is a German word that means opposite. Um, and the short for that is E. So we would say that this configuration or this stereochemistry is E olefin. So the name should be italicized E 4-bromo-3-heptene. Now, kind of like what we did with RNS, if there's more than one double bonds in the molecule, you should indicate which double bond is the E configuration by putting a number in front, like 3E 4-bromo-3-heptene, but since there's only one double bond in here, you don't have to put the name. Okay. Or sorry, put the number on. Now, I want you to know that cis and trans can be substituted by Z and E or EZ configurations as well. In this case, right, it was cis. We could also call this Z, or zusammen is the German word for together, kind of like cis, because on this carbon, the higher priority group is this instead of the hydrogen. Here, it's again the carbon instead of the hydrogen. The highest priority groups are both on the same side of the double bond, so it's zusammen or Z stereoisomer. And then, of course, this would be also E. So hopefully that makes sense. And we'll, of course, do some practice problems during class. And if you have questions about this, which I'm sure some of you do, please raise those during class. Now, I don't know if this is helpful to you or not, but I keep saying this, but one of these days, I'd love to buy or make this t-shirt. That would be great for like an Alchem class t-shirt. Anyway, one of the other things in this chapter that we should discuss is how to prepare alkenes. And there's basically two ways. There's kind of a third method that we will not discuss in this semester. The first method is elimination reactions, right? Like if you had leaving group on an alkane, and if you have a strong base, you could do, in this instance, E2 reaction, or you could also do an E1 reaction if you lack a strong base, right? So E1 and E2 reactions, we've discussed those back in chapter 7, so I would just refer you to those notes. So elimination reactions give us olefins, alkenes. Now, another method is reduction of alkynes, and remember that's the triple bonds, right? Triple bonds can be reduced to the double bonds alkenes by these different methods that give you different stereochemistry, cis and trans, but we're going to discuss these in detail in chapter 13, so we'll just, won't discuss those in detail until then. The third method would be Wittig reaction, which will not be discussed during this semester. So yeah, I don't think you need to worry about that this semester at all. So in the next few videos, we're going to be discussing infrared spectroscopy and mass spectrometry, both of which can help us identify functional groups like alkenes in the molecule. So this is kind of gets into a really exciting territory for especially those of you who are more analytical oriented, or I hear that some of you have like interest in like forensic science or forensic chemistry. These are very common analytical techniques used in those areas, as well as if you work as a medical scientist in a lab, analyzing urine, blood, that kind of stuff. So we'll get into stuff like that. See you in those videos.